Good morning. We're Team SPARC, and we've built a robotic, autonomous, solar-powered boat. I'm Sawyer, and these are my teammates Cristina, Sebastian, and Emily. 71% of the Earth's surface is covered in water, but we have yet to explore 95% of this area. Researching it is critical for understanding biodiversity, climate change, severe weather patterns, and more. Currently, the only way to do this is to send out a manned voyage, which can cost from $20,000 to $50,000 per day. Today, a new market of autonomous solutions is rising that will help us explore the ocean more safely, cheaply, and effectively.
SPARC is a low-cost boat that serves as an adaptable oceanographic research platform. It is solar-powered and autonomous so that it can remain operational for indefinite periods of time, and it features a precision electric winch that can deploy a sensor module so that data can be collected at varying depths. This data can then be transmitted back to shore so that it can be used without the need of retrieving the boat.
SPARC is a versatile research platform with applications in a variety of industries, from oceanography to water quality to oil. We've worked hard throughout the year to build a product that can be useful to all of these customers, and our research includes conversations with managers and engineers at ExxonMobil, scientists at the Scripps Institute of Oceanography, and ocean roboticists at the Monterey Bay Aquarium Research Institute.
SPARC's value is measured in data gathered per cost per day. To maximize its performance, we've maximized all the data that we're gathering, the travel speed, and minimize the system's cost. As Sawyer said, manned voyages cost upwards of $20,000 per day. One of our competitors, another autonomous research craft, decreases that cost, but we still think it's unnecessarily high. SPARC, on the other hand, costs half of 1% of those manned voyages. So at that price, you can buy an entire fleet of SPARC boats for the price of just one of our competitors.
This is SPARC. We'll show the key features we designed into it here, and we'll take you through them one by one. I'll start by talking about the boat structure. Low cost and adaptability are two of SPARC's most important value propositions. For this reason, we try to use standard components as much as possible while still ensuring that they're corrosion resistant. You can see here we have a pontoon structure, which is made out of PVC, and the aluminum frame is reinforced with fiberglass sheets so that it can remain low cost, but still very strong. It is important to scale the size of the boat to fit different requirements. For this reason, we have an easily adaptable parametric SolidWorks model that we can simply change values and make the boat a different size for different requirements. This all depends on key relationships between dimensions that were calculated based on dynamic simulations to ensure structural integrity and stability. We estimate the cost of SPARC to be around $5,000. We've iterated through many prototypes to get where we are now. We started with a very simple wooden frame and small pontoons. Since then, we've increased the boat size, switched to better materials, added motors and electronics, added the sensor module and the winch, and implemented solar power and navigation controls. The pontoons can be seen here. They have two motors towards the back of the boat, each of which can provide 30 pounds of thrust. These are off-the-shelf trolling motors used for boats. And steering is achieved through a differential drive, meaning that the propellers can spin at different speeds or sometimes in different directions. Because of the amount of, we want SPARC to be able to travel at 2 knots continuously, and we need 10 pounds of thrust to achieve this. Because this will give us a propulsive efficiency of 63%, but we're looking into ways of reducing this by reducing drag, by increasing the efficiency, by reducing drag and using bigger props. Because power is proportional to force times velocity, but drag force is proportional to velocity squared, it is way better to travel slowly through day and night than to use all the solar power during daytime.
Under the boat houses a waterproof control box, which can store 1,200 watt-hours of power in our lithium-ion battery to store this power for continuous day and night travel. This is the inside of the control box. Inside, we house 2 Arduino microcontrollers, motor drivers, and a cellular modem for wireless communication. An XBee wireless radio is used for short-range communication. A GPS module connects to an external GPS antenna, and we use current sensors to monitor power and performance of the boat at all times. Everything connects to the main board with a PCB that we designed ourselves in Eagle and sent out for fabrication. The charging system provided by Gridless Power features a maximum power point tracking charger, 2 voltage regulators, and the 1200 watt-hour battery. A switch bank inside allows us to turn off each subsystem individually for debugging purposes. As you can see to the upper left, there is a panel that allows us to connect everything from the outside of the boat inside the control box, and everything remains waterproof. This solar panel charges the boat for 24/7 travel. As you can see here, SPARC travels night and day, and we've simulated power in the boat for a week. During the daytime, the battery is charging, and at night, it's discharged. If we ever have excess power, that goes right to the motors, and if we ever don't have enough power, we can turn off the motors to conserve power.
SPARC's winch and deployable sensor module allow it to explore more than just the surface of the ocean. We're particularly interested in exploring the thermocline, a layer of water where temperature and many other properties change very drastically with depth. To do this, we've built a precision electric winch, shown on the screen up here, which consists of 250 feet of cable attached around a strong Delrin spool and turned by a motor to its right. That winch, the cable is deployed using a nylon pulley. This pulley allows us to mount the winch horizontally under our boat while still deploying the cable vertically into the ocean. This spool in the inside also has the cable connected to it through a slip ring so that an electrical connection can be made to the control box. We also made a sensor module, and this sensor module is plug and play, which means that us or anyone else can add whatever sort of sensor module they want. We know that SPARC's biggest perk is that we're adaptable, so working with any company and being able to put their own implementation on there is very important to us. This current sensor module has measurements of temperature, pressure, water color, and salinity. To make sure that the solar panel is facing the sun always, we had to come up with a very unique design to make sure that if it did get flipped over, it would not stay that way. To do that, most companies use a large, heavy keel under the boat. Well, we found that it would greatly increase our drag and the overall weight of our boat. So we decided to invert that keel to the top and add inflatable fenders to the top. The inflatable fenders allow it so if it does flip over, the buoyancy is enough that it'll flip back to a horizontal position, and then the weight of the boat will take over from there and flip it all the way back upright. This MATLAB simulation shows what happens if the boat flips over. The green is the buoy, and the red are the pontoons. We also simulated this at a scale model in the Potruck pool very early on. We feel that all these features make SPARC truly unique, and we really believe that we've built a robust and adaptable design. We first started testing in Potruck pool in October. There, we tested what frame was the right requirements, what reinforcements we did need for that frame, and we did some preliminary motor tests as well as some drag calculations, as you can see on the screen. From there, we worked up to testing in the Schuylkill River. There, we tested our control algorithm to see if our boat could follow a compass heading, which you can see it's following now. And finally, we have our last test where we had full controls implemented and the boat was following a set of waypoints with GPS coordinates. Each of these tests were very challenging, especially transporting such a large boat, but we think they were highly essential in the final development of the boat.
SPARC's architecture is best described by 3 main blocks: the central control system, a separate charging system, and the sensor module itself. At the heart of the control system is an Arduino DUI, which is responsible for navigation and control. It's connected to a GPS and digital compass, as well as a host of current sensors that allows it to monitor the boat's power consumption, and it's also connected to an Arduino Mega, which is responsible for cellular communication through a cellular modem and data storage on an SD card. The separate power system is mostly donated by our generous sponsors, Yingli Solar and Gridless Power. And the solar panel plugs into a maximum power point charger, which ensures that no matter how much sunlight the solar panel is getting, it's running at maximum efficiency. This charges a 48-volt lithium-ion battery, which then connects to two voltage regulators to regulate 48 volts down to 12 volts for system use. The sensor module itself consists of an Arduino Uno attached to various sensors, which is logging water temperature, pressure, salinity, and water color. It logs this data to an SD card when it's under the water, and then when it's raised back up to the surface, it waits for a request from the control box. Then it transmits this data wirelessly back to the control box using an XB wireless radio for later transmission to shore. All of the data that SPARC collects is sent with a cellular modem to a FTP server that we set up on Amazon Web Services, which allows multiple SPARC boats to be connected to the same computer and to the same server, and multiple users to access this data. This opens up, while this means that SPARC can be used individually, of course, it also opens up exciting possibilities for using SPARC as a fleet, one of which we've outlined here. SPARC could be used as a fleet in the Deepwater Horizon oil spill, which covered 60,000 square miles and cost $32 billion. 250 SPARC boats, each traveling at the mere speed of 2 knots, would be able to cover this entire area in just 5 days, while using their deployable sensor modules to generate a 3-dimensional map of the oil plume under the water. Having this map would help researchers and cleanup efforts best decide where to focus cleanup and containment. So even if at an estimated cost of $2.5 million for those 250 SPARC boats, which is still a drop in the bucket compared to the total oil spill cost. By making cleanup and containment slightly more efficient, the fleet would more than pay for itself.
We have future plans for SPARC, which include optimizing certain components for efficiency, getting the boat ocean ready, and adding increased sensing capabilities. All this together will lead us to a pilot program where we hope to provide at least one boat to an oceanographic research lab, and we're currently actively seeking recommendations, funding, and support in this endeavor. SPARC is obviously a very expensive senior design project, and we've generously received a lot of support from all the people shown above. And we'd like to acknowledge all the people who took a lot of time out to help us throughout the year. Thank you so much. Many of you are in this room. Thanks for helping us make this reality. And next stop, we are headed to Disney World later today to compete in the Intel Cornell Cup, a National Embedded Systems Innovation Competition. So thanks again for your time and wish us luck.
We will now take questions.
The cellular modem is the means of communication, and in many places I would assume you won't have any cell signals. How much data can you store, and if you lose power, do you lose any of the data?
The data storage depends on the SD card size, which is easily removable. Standard off-the-shelf SD cards in today's world can go up to 64 gigabytes, 128 gigabytes. This is a pretty huge amount of data. Another issue, as you mentioned with the cellular modem, is that it doesn't have service in a lot of areas, and moving forward, we're going to be replacing it with a satellite communication device, which is going to help us move farther out from shore and just generally be a more robust system. Yeah.
Have you given any thought to what your system is capable of in cool weather conditions, or what you would have to do to make it handle heavy storm systems?
So that raises a couple of, poor weather raises a couple of problems. The first is severe waves, and we've designed the frame to be strong enough so that no matter how strong the wave, the maximum force being exerted by either pontoon can't damage the frame. It also has the problem of, meaning there's increased cloud cover and rain. And as you saw in that power simulation, when the power levels drop for sustained periods of time, the boat stops traveling until it can recharge its system and just maintains its communication with shore.
Can you get it out to search for that plane?
We would like to.
Thank you very much.
Thank you.